Fine, all of you, right?
Yes.
Good. So what I intend to go through over the next hour, 15 minutes or so, is how modulation and coding techniques have, mostly coding techniques, not so much modulation, how modulation techniques have evolved in digital wireless communication, particularly with regard to the wireless LAN system, not wireless LAN, but the 3GPP systems, which is the WAN systems, wide area network systems. Um, so roughly, I will talk about how wireless standards have evolved, the theoretical background and the coding techniques, and I was thinking of originally talking of modulation as well, but realized that this is probably too small a time to do both. So we'll just stick to coding. And in the end, I'll try to leave about 15 minutes for question and answers so that, you can, any question you can ask. Also, during the presentation, at any point, if you have any questions, feel free to stop me and ask me. That's perfectly fine by me. Um, so if you look at how wireless standards have evolved, you know, on one hand, there is Wi-Fi, and on the other hand, there's the wide area network. This is roughly the timeline over which things have evolved from what we called 1G, which is the first generation systems, which involved analog communication mostly. So AMs and stuff like that, which evolved slowly to a TDMA system of GSM, and then the 3G systems, which was initially CDMA 2000 in North America and spread as UMTS and WCDMA over the rest of the world. Up to beginning of 3G, most of this mostly concentrated on voice. So voice was the main thing. People talking on cell phone was the biggest thing. And then slowly data started to proliferate around the 3G timeframe, to the point where, iPhones got introduced, and that really was, I would say, a watershed almost, because from being mostly voice traffic and little that data traffic at that point, it became largely data traffic, to the point that 4G systems did away with the circuit switched part at all. So voice became packet switched starting in 4G, which is the LTE systems. And of course, it's all IP network in 5G. And slow, as you can see, the data rates have slowly increased, from being a 2.4 kilobit per second, we are talking of 1 megabit per second on an average here. Wi-Fi systems also have evolved in parallel. There have been 5 generations of Wi-Fi systems, starting from basic 802.11 to what we call 802.AC now, where we have gone from a single user system, to a MIMO system. Also, some of the paradigms of how Wi-Fi works have been little changed. However, I am not going to spend too much time on Wi-Fi. I'll mostly spend time on CDMA 2000. So all of you are familiar with this. I will not spend much time on this, but basically we say that Shannon's capacity formula is W log 1 plus P by N naught W. So the minimum bit energy you need for reliable communication is given by this quantity, where if you call C by W as eta. Of course, when there is infinite bandwidth, we can take the limit as eta max goes to 0, and then we see that you need a minimal of minus 1.59 dB, which is the minimum SNR for 1 bit of information transmission. Now, Shannon's theory says that if you have a discrete memoryless channel with maximum likelihood decoding, then the FER of a length encode with rate k by n is given by this quantity, which is exponential of minus e to the power n ER. This ER is a convex decreasing positive function which satisfies that RC should be less than C. So from this equation, what can we do? To reduce SNR, to reduce FER rather, we can increase channel capacity, which is effectively increasing the SNR. We can decrease the code rate, or increase the bandwidth, or increase code block length, because we have this dependence on this parameter n. Now, increasing channel capacity is something that we can't really do much, because we can increase SNR up to a point, but then we are power limited. So there's a beyond a point we can't really improve power, and noise you cannot do anything about. Noise, whatever there is, there is. So the total power of noise you can't change. You can increase power up to a certain point, but in digital communication, especially in wide area networks, just increasing power blindly always is also not the correct answer, because it causes interference to everybody else. So there's a trade-off. So you can do it up to a point. Code rate we can decrease, but the more you decrease code rate, the more you increase the overhead. And so the amount of effective transmission data rate goes down. So you you want to do that up to a point. And code block length can be increased. However, the longer the code block length, typically it will take you longer to send, because the bit per second per hertz you can send is certainly defined by the chip rate of the system. So you can do this up to a point, and of course, first one, it increases delay, and second, it increases complexity. Now, if you look at the capacity curve of these functions, you can see that with arbitrary input. So what I've plotted is bits per second per hertz on the y-axis, which is the spectral what do you call? I'm sorry. So basically, spectral efficiency. This is the spectral efficiency of the system, and the ES over N naught, or symbol SNR on the x-axis. If it is unconstrained, of course, you have the capacity curve increases. If you do constraint modulation, in other words, you are doing 64 QAM, so you're sending 2 bits per second per hertz. Sorry, 64 QAM, you're sending 6 bits per second per hertz. But for BPSK, for example, or QPSK, which are equivalent, you're sending 2 bits per second per hertz, so your capacity will be constrained at 2 bits per second per hertz. And similarly for 18 QAM and 16 QAM and so on. So this is roughly the capacity chart. Question is, how close can we come to capacity? Shannon says that as long as you are operating within your channel capacity, you can achieve error-free communication by doing random codes. What are random codes? He says basically choose a code rate k by n and then code up bits randomly. Just add random parity checks and it will work. Well, you try doing that in real life and you very soon realize that, this will work when the block length is very, very, very large, in fact, approaching infinity. If you look at the proof of the theorem, in fact, that is how Shannon argues that when the block length goes to infinity, indeed, that is what we get. However, the folk theorem is all codes are good except the ones we know. So none of the codes that we seem to know ever seem to achieve this capacity. And that was roughly true till the 90s, where we would say that there was a long-standing conjecture that there's a cutoff rate, which is 3 dB from Shannon, and you can't really get any closer to that. The other problem with random coding, of course, is that then you need a structure. It's okay to say that there'll be a random coding and I'll decode it, but then how will you decode it? If you have encode words, then you have to go through all of these, and if the block length becomes very, very large, the amount of time and the memory needed to go through all of these and choose which one is the correct one is extremely large. So you need something where you're trading off memory and complexity and be efficient about it. However, this long-standing conjecture of this coding bound was proved wrong by the introduction of turbo and LDPC codes somewhere in the 90s, which came to tens of dBs within Shannon bound, and polar codes more recently, which say that asymptotically these are capacity achieving codes. Okay, so these two things have kind of changed and have breathed new life into coding theory. Now, it's one thing to have a theory, and then another thing is to really put it in practice. So to put it in practice, you have to put it in the context of what the wireless system is doing at that point, or what is the goal, does the system operate, and so on and so forth. So let us look at pre-4G systems. I will not go into AMPS and GSM and all that because those are way before all of this. Most of this development was later. So let's start from WCDMA. And also, since 3GPP2 doesn't really exist today, I will concentrate most of my talk on WCDMA or 3GPP. So there were two standards bodies, the North American body of 3GPP2 and the European body at that point, Europe and Japan and everybody put together 3GPP, which soon became replaced as the worldwide standard, which is good. We didn't have a VHS Betamax kind of a thing that happened with the video cassettes and stuff like that. So let's only look at those standards that happened. So if you look at the evolution, Release 99 or WCDMA was the first interface that was defined. It was mostly an FDD interface, and then TDD was also defined at a later point, which dealt with circuit switched voice for the most part and some packet switched data on top of it. Then we went to different releases, what was known as Release 5 HSDPA, Release 6 mostly HSUPA, and then HSPA evolved and HSPA Plus in Release 7 and 8. So HSDPA mostly introduced a high-speed data along with voice. So from 384 peak, which was mostly circuit switched, we went on to a peak of 1.8 Mbps to 14.4 on the uplink. The initial focus was only on the downlink, so that is why Release 5 is the HSDPA. Then Release 6 was HSUPA, where we improved the uplink as well. At this point, multicast was also introduced. And then HSPA worked with enhanced voice capacity, MIMO, and so on and so forth to increase this all better. All this was CDMA. So all of HSPA was CDMA. Whereas with LTE, which was a track that was developed in parallel, it was the OFDMA system. One of the main reasons of going from CDMA to OFDMA was really two things, I would say. One, with increasing bandwidth, to maintain a synchronization across the whole bandwidth becomes harder and harder because there's frequency selective failing. So as a result, to operate CDMA, so most of this WCDMA system was 5 megahertz systems. To operate at 20 megahertz, we went to so-called multi-carrier systems. So there were multiple 5 carriers, 5 megahertz systems. OFDMA, on the other hand, since each symbol is quite small in frequency, the footprint is very small in frequency. They're still coherent, and so you can still go ahead and do a one-tap equalizer at the receiver for them. And the advantage with one-tap equalizing is when you are doing this in conjunction with MIMO, the number of taps times the order of the MIMO is suppose that number is n, then you have to invert an n cross n matrix for MIMO processing. So if you have a CDMA channel, you would have a long equalizer, which would increase the order of the matrix inversion to be done, which is an n-cube inversion roughly. So that is why we slowly migrated to OFDM, and that's what LTE is. So in 3G systems, as we talked about, that we went from voice to data. Now with 5G, there is a whole lot of new verticals that are involved. If you had to look at 5G, I would say there are roughly 3 areas that 5G went in, which is EMBB, which is enhanced broadband, that is for larger data rates. The second is for ultra low latency, URLLC, which is things like if say you are doing autonomous driving, a doctor is doing a remote operation or what have you, where that delay is extremely critical. And thirdly, for machine-to-machine communication, which is MTC, machine-type communication, where the data rates are extremely low, but there are huge numbers of connection, and maybe even the duty cycle is quite low. So now, when you talk of, say, data communication in in 3G or 4G. Typically, the way it works is that in the physical layer, you need a rather low error rate, but that error rate is roughly in the range of 1% or so. So voice works reasonably with the 1% error rate. With data, we typically have hybrid ARQ, which is you send the packet again with incremental redundancy till the packet is decoded. Now, when that happens, the first transmission error rate, if you are looking at a 1% final error rate for the data, because there are upper layers on top of that. Remember, this is only the physical layer error rate. So on top of that, there's the MAC and RLC and so on and so forth. And then there's IP. So by the time it goes to the IP layer, the data rate is quite small. But the physical error rate, we can choose to be 1% out of the physical layer. So the first transmission error rate can even be more than 10%, even if you're transmitting two transmissions, if you're targeting two transmissions. However, one thing that we'll see is that turbo has an error flow, turbo codes have error flow, and LDPC do not. But this error flow occurs like 10 to the power -4, -5, or lesser, depending on the turbo code. So that really never was a troublesome when you talk of 4G systems. But when you talk of 5G systems, when we are talking of this extremely low latency and extremely low error rates, then it becomes an issue. So that is something to remember. So as a result, we have a whole lot of choice of which codes to choose. There are all kinds of block codes, the well-known BCH codes, Gole codes being the only perfect codes that we know. Reed-Muller codes, Reed-Solomon, Hamming. By perfect codes, we mean that the spheres are perfectly packed. But I will not go into that. Never mind. So block codes, these work well for small block lengths. Not that they will not work well for large block lengths. The problem with large block lengths is to decoding, you need too much high memory and complexity. Extremely good thing is that they have no overhead involved and lots of good codes involved. Convolutional codes have been known to do much better at medium lengths, say 50 to 200 of block size, which is ideal for voice. So when you talk of voice, those are typically the frame lengths that you are talking about. For very low rate, the overhead is too much because the the decoder needs to be flushed out. And so unless you do a tail biting code, which leads to additional complexity. And if you become very, very high, so block lengths of 5,000 or so, performance is not as good. Where somewhere, depending on who you ask and how you simulate it, which kind of conditions, you'll see that turbo codes start performing better than convolution codes somewhere in the 100 to 100 block length range, and keeps getting better and better as you increase the block size. So, but it has higher computational complexity. LDPC code is very similar in performance to turbo codes, except for this error flow stuff that I told you about. However, it does trade memory for complexity. There's more memory involved in when you try to decode an LDPC code, but the complexity is much lower. And finally, the polar codes are asymptotically capacity achieving. They are large block lengths code, and the way it was initially proposed, it was successive cancellation decoding, and then we have modifications on them that we will soon see. So now, depending on what application you have, what application you had in mind, you have to choose one of these proper codes to go with it. So what are the things that we have? Sorry. Let's see in 3GPP, what are the things that we have? We have control channels and we have data channels. So control channels are typically small and convey a small amount of information. So for those control channels, obviously block codes are a good thing. For data channels, there are two kinds, either is voice or data, at least in the initial 3GPP systems. So for voice, of course, convolutional codes would be a good choice. For data, on the other hand, which is typically large length, people use turbo codes. Then as we came to 5G, turbo codes were replaced by LDPC codes, and much of the block codes were replaced by polar codes, particularly for the channels, control channels. We will see this when we come. So let's start with the simple codes that are there. Obviously, the simplest code is a parity check code where you add a 1 bit of parity. I won't go into any of this, but obviously, here you can only detect errors for a very marginal increase in code rate, so your overhead is extremely small. On the other hand, if you do repetition code, by the way, repetition code is there for ACK channels and stuff like that in 3GPP. We use that. You can have a code rate, say 1/3, then the overhead is 200%. But of course, using majority logic decoding, you can correct all single errors. So obviously, we should be able to do something smart, in the middle where we can detect some amount of errors without incurring so much overhead. And the block codes do exactly that. So typically, the way the block code works is that you have an input k tuple and an output n tuple with r parity bits given by n minus k. The encoding is done through a generator matrix, which is k cross n, so that your code word is UG. So a binary code typically will have r parity check equations of the form that I have shown you, where the plus with means the modulo 2 addition. There are various kinds of codes that are known, and very often we use a systematic code where the generator matrix is partitioned into the parity bits and the information bits, where the information bits are sent without any change, and the parity bits undergo these parity check equations. Codes can be linear or nonlinear. Linear means that the sum of two code words will also be a code word, and the most powerful of that is the branch of Reed-Muller codes. Or there can be cyclic codes where all cyclic shifts of the code words are also code words. This fall in the class of BCH codes. And all these have the effect that they lead to good decoding algorithms. Parity check matrices are row by n column binary matrices, where the rows represents the equations and the column represents the digits in the code word. For example, the Hamming 7/4 code, the parity check matrix is as shown, and you know all of this, so I'm not going to spend any time. What is somewhat important though is that for a generator matrix, G and H are orthogonal. So C is a code word if CH transpose is 0 and hence leads to an efficient decoding algorithm. So instead of doing on each, you can calculate the syndrome, and from that syndrome, which is the CH transpose, you can find which is the closest code word you have so that you can map it to that code word. So if the smallest Hamming weight is so-called the minimum distance, this being a linear code word, the code word with the least number of ones, the number of ones is the minimum distance, because the codes are, as we said, they're linear, so you can add one to another. So as a result, you can always add one code word to itself to generate the 0. So you can look at the minimum distance from 0 so that the error correction capability is the floor of d minus 1/2. The class of codes of these in particular, which are used a lot in 3GPP, is this class of Reed-Muller codes. These are a set of binary codes which consists of all polynomials of m variables of degree less than equal to 2. And if we have all binary length m vectors, we can form a Reed-Muller code MD in general of order D. For example, all 16.5 and 32.10 codes are used in 3GPP. In general, its minimum distance is 2 to the power m minus d, where it's a linear m and 1 plus MC1 plus MC2 plus MCD code. Cyclic codes are also fairly used often in 3GPP, where every right cyclic shift of a code word is also a code word. These are easy to generate with a shift register, and you can have good decoding algorithms. LFSRs are used, and important examples are BCH codes, Reed-Solomon codes, quadratic residue codes. Most of these are used in CRC. So with all data in WCDMA and so on and so forth, you append a bunch of CRCs. So that after you're decoding with the CRCs, you can make a decision as to whether the frame was correctly decoded or not. So if you add in n bits of CRC, the probability of a random sequence passing that bit is 2 to the power minus n. So that's how you choose n as to how many CRC bits you're going to have. The next important class of codes are the Reed-Solomon codes, which are maximum distance codes over GFQ, Q being p to the power m. As you know, any finite field, to be a finite field, it has to be modulo addition sum prime. So addition is defined on the base field modulo sum prime, and on the base field, you can do multiplication, and on the extended field, which is p to the power m, which can be thought of as a m tuple of vectors, m tuple vectors, that is, with each being a base p operation on the field. Otherwise, you cannot have a field. You can show that one of the actions fails. So in particular, in any field, we got to have that that the product of two non-zero elements must be non-zero. This will fail if you don't have a prime. As a result, we are forced to do these minimum distance codes over GFQ, and these are length q minus 1 codes. So if beta is a primitive element of GFQ, what does a primitive element means? It means that beta, beta square, beta cube, all the way beta to the power p to the power m minus 2 form all the elements of the field that are non-zero. Of course, you cannot generate zero out of this, but you can generate all the non-zero elements so that p to the power m minus 1 elements are generated by this, so that beta to the power p to the power m minus 1 will be equal to 1. The Reed-Solomon codes of minimum distance 2 is given by this certain generator polynomial that I've written. The polynomial coefficients in general are not guaranteed to be in the base field if you do this. However, if you look at the code that is used in CDMA 2000, in WCDMA, which is what I have shown, you can actually choose your polynomial in such a way that they do lie in the base field, which helps in some decoding algorithms. Just efficiency. There are also, we can do what is known as shortening or erasures are two things, because one of the things that happens is that although these codes are defined only for certain block lengths, in real life the block lengths are not fixed, so they change much more than the codes allow them to change. So one of them is to just puncture some bits from the output to generate the length that you want. And when you decode, you just treat the puncture as a erasure. So your log likelihood ratio you put in as 0. If you put the log likelihood ratio as a 0, it's basically an erasure, and you depend on the error correcting capabilities of the code to get to the correct code. So as I said, convolutional code was a very important part of the communication systems, particularly in 3G and 4G. Convolutional codes are used for voice for the most part, and certain tail whitening convolutional codes were also used for the control channels in 3GPP. They're generated by a finite state machine, and they can either be recursive or non-recursive. If it is recursive, then the output is fed back into the input. If it is non-recursive, then it is not. Now, most of the convolutional codes that are used in standalone, in fact, all of them are always non-recursive. Why are they non-recursive? Well, the thing that happens is that if you have a non-recursive convolutional code and a recursive convolution code with the same constant length, what is meant by the constant length is you use a number of shift registers to generate the code. For example, here is an example that is shown on this page where the constant length is 3. The code rate is half here, so for each 1 bit input, you get 2 bits output. And at the end, after you have sent in all your data bits, you need to flush out these so that when you put in new data, you start from 0. If you do not, then you have to try some other techniques that you have to look at all the possible states that this could be in and decode across all possible states, which then leads to additional complexity. It is possible to do that. They're called tail biting convolutional codes, but in general, the convolution, in fact, tail biting convolutional codes are used for some of the control channels in 3GPP. But for data channels, particularly voice, what we use are convolutional codes where we flush the buffer. So they're not tail biting. Zero forcing. They're called zero forcing convolution. So these generated functions, for example, in this case, are two generated functions for the two streams. One is simply x, where you send the code word address. One is 1 plus x. The efficient way to decode all of this is through the VITERBI decoding algorithm, a dynamic programming algorithm that you are all familiar with. I'll not spend time in this, but if you have 0, 0, 0, 1, 1, 0, so if you start from the all zero state, there's only a couple of states you can go to and so on. And that way you can form a whole trellis diagram and pick your optimal path through your maximum likelihood decoding, which is a dynamic programming algorithm. Of course, if you retain all the paths, it becomes very difficult. So what you do is at each stage, you retain L paths. Okay. So not all of them, but certain number of paths, say 8 paths or so on and so forth, which is sufficient because most of the time your errors, the probability of your actual code word being outside all of those paths is rather small. So remember this, because when we talk of polar codes, will come to this. So VITERBI decoding basically is a dynamic programming algorithm where at each stage, the most likely surviving paths of minimum weight are kept, and we repeat it for the next stage. The output is the most likely path at the end of the trellis, and you can either do zero tailing or tail biting, as I told. If you look at the convolutional coder that was used in CDMA 2000, which is the North American system, these are length 9, constant length 9, k equal to 9 convolutional codes of two kinds, rate half and rate 1/4, that were used. So this is the convolutional code structure that was used. And the corresponding structure in WCDMA is given by this. One is a rate half and rate 1/3, both are constant length 9. So this is just examples. Now, what happened was from 3G systems, we came to 4G systems. Now, 4G systems, as I said, from our LTE systems, they're an OFDMA and peer interface with a scalable bandwidth. And MIMO was introduced from the initial stage. So initial 3G things didn't have MIMO at all. In later stages in HSPA, MIMO was introduced, but LTE MIMO was introduced from day one. However, there's still an ability to do MIMO or not MIMO. There are in fact 7 MIMO modes which exist in LTE, the original LTE release, and then subsequently there have been more MIMO modes added after that. So single input, single output is definitely an option, but the assumption in LTE is that the receiver at least has 2 antennas. Even though the system can operate with one, most of the performance is written in such a way that at least the receiver has 2 antennas. This is an all IP network, so it's packet switched with no CS. Initially, CS meaning circuit switched. Initially, voice, there was some legacy interworking so that voice could be circuit switched. This was called circuit switched fallback and so on and so forth. But native LTE voice goes to an all IP network. Then in release 9, there were some additions, in particular broadcast, although that never saw the light of the day. And then in release 10, we went to enhanced MIMO and in particular support for heterogeneous network. Carrier aggregation, which was the most important thing, that from a 20 megahertz bandwidth. So LTE release 8 and 9 allowed up to 20 megahertz bandwidth. LTE release 10 allows you up to 100 megahertz bandwidth, so up to 5 carriers. And then as we went forward, there were more sophisticated techniques like coordinated multi-point transmission and so on and so forth. And then we go to pre-5G system beyond release 12 and so, and that we'll talk of slightly later, because really release 10 LTE still says deployments. Beyond release 10, only very few features of LTE actually have seen deployment, and most operators, instead of going for LTE release 10 deployments, choose to go straight to 5G with them. The most important thing in release with LTE was that the data channels now went through turbo codes. There was also turbo codes that were used in WCDMA and stuff for data channels. But here in LTE, this was the only one that was allowed. Turbo codes actually breathed a new life into coding theory and got rid of this phantom, this coding bound, this cutoff rate business. In 1993 in ICC, the result was published, and it was shown that it was within 0.5 dB from Shannon capacity. They have parallel or serial concatenated coding with recursive constituent convolutional encoders. Now, I just said when we were talking about convolutional coders that we never use recursive, and I didn't elaborate on that. So let me elaborate a little bit on that here. If you look at the distance profile of a code, what is the distance profile of a code? That if you have, let's say, k code words, out of those k code words, k1 has distance d1, k2 has distance d2, and so on and so forth. Then this d1, d2, dj is the distance profile of the code. And when you're talking of any encoder, the minimum distance is all that matters. So whatever is the minimum of this is known as the minimum distance of the code. And that is what gives you the error correcting capability. Because if there is any code less than that, then the minimum error capability is decreased, the error correcting capability. Now, when you talk of a convolution encoder, obviously you want this minimum distance high when it's a standalone code. And that is typically what happens when you don't have recursive codes. With recursive code, what happens is this minimum distance becomes lower, typically. Again, these are general statements. That's not true for everything. But in general, the minimum distance goes down a bit. However, the maximum distance also increases. So the profile, instead of being somewhat flat, so if you look at a non-recursive code, it's a somewhat flat distribution profile. There are few at D1 and so on and so forth. Now the profile becomes quite different. So the high code words are protected very well, whereas some code words get very low protection. Why would we want to do that? Well, the reason is when we do turbo codes, what we do is we take the input bits, we pass them through one recursive convolutional encoder, interleave them, and then pass them through another. So now, if you think of the interleaving as being perfect random, in all probabilities, what happens is as long as the block length is large enough, and the interleaver is good enough, that is why you need a very good interleaver. What has been protected badly through one particular encoder is being protected very well through another. Okay. So as a result, if you take the minimum distance as the max of these two, because that is what, if you have two independent decoders, that's what they're going to do, then of course the protection becomes better overall. Whereas, can you guys still hear it okay?
I think so. More or less, it's fine.
There are problems. Okay. So let me continue. What happens then, since this profile has changed, that is why we use this benefit while we're doing turbo code, while we could not have done this in the VITERBI coding for a standalone convolutional code. So what we do then is that we do this interleaving and an iterative decoding, which is really a maximum a posteriori decoding bit by bit. I will come to that in a little bit. What we know is that we need a good set of interleavers and a good recursive constituent code. What we do not know is why this decoding procedure today there is no good explanation why this decoding procedure works the way it works, why it converts. Because we know of turbo codes where this actually diverges. Let's look at how what this looks like. And this is a parallel. In case of serial, the interleaver, the constant encoder, interleaver, and the two would be in series. And we have a bunch of parity bits. We puncture them and send them. This is how we generate the turbo codes in CDMA 2000. In coded system, of course, a good code will produce uh, a, a low weight outputs with very low probability. And a recursive systematic codes will produce low weights with fairly low probability, but then the interleaver will make sure that these are roughly mapped to high weights in the other one. So parallel concatenation of both encoders typically produces a good code, as I explained to you. And this is what is used in WCDMA, where there are two constituent encoders, and the outputs are as shown. So as you see, they're both constant length 4 encoders, and it's a base code rate 1/4. As you can see, there are 4 outputs. Now, beyond that, you can certainly do your puncturing or shortening and whatever. So now, in general, when we talk of decoding techniques, we have 4 different decoding techniques, roughly. For VITERBI decoding, we do what is so-called maximum likelihood sequence decoding. So we have no a priori information. We have no idea initially what the bits could be. We just assume them that they're equiprobable. And then you take the whole sequence and figure out which sequence was most likely to have yielded the output sequence. And that's your answer. Okay, that you decode it like this. If you have no, you can also do a map, which is the maximum a priori sequence detection. So if you knew, suppose that some code words were more likely than others, you could use that information and use your conditional probabilities. From the conditional probabilities, you can go to the total probabilities using that a priori information. You can do maximum likelihood symbol by symbol. So each symbol you could do this, but this is obviously suboptimal. Although it's suboptimal, it's very, very quick in the sense that, then you're basically each LLR you take on each bit, and whether it's positive or negative, you declare it 1 or 0. This is essentially bit by bit. Or you do turbo decoding, where what you are doing is, in the first stage, you do this map decoding. And then each bit, there's a certain probability. You feed these probabilities back. So the probabilities of the first is constituent encoded is fed to the second, and the second to the first. And then based on this, you do a map decoding again. Obviously, the map, this would be even better if you could do map sequence decoding instead of map bit by bit decoding. But it is too complex to implement today. I mean, if you think about it, LDPC was introduced by Gallagher in the 50s, and it was not done because it was too complex. Today, it's not too complex. It's perfectly fine. So someday in the future, probably map sequence we can do. However, today, as it stands, map sequence is too complex, and so we do map symbol by symbol in turbo decoding. So this roughly covers 4G. From 5G, what has happened is, I told you that there are three main things, which is enhanced mobile broadband, higher reliability control, and wide area Internet of Things. If you look at the whole idea of 5G is that we are trying to encompass a whole branch of different applications, a whole bunch of new verticals that this technology is getting into. So with wide Internet area of things, we are trying to get deeper coverage, lower latency, lower complexity, and higher density. Now, higher density also applies to enhanced mobile broadband, where the whole idea is to get enhanced capacity, enhanced data rates, better awareness, and then frequent user mobility or no mobility at all in terms of high reliability control. Of course, when you're doing data, you are very often mobile, but sometimes the kind of things I talked about, say a surgeon doing an operation, no mobility is required. But what is required is a tremendous high level of accuracy and extremely low latency. So we are talking of latency less than 1 millisecond and a huge strong security. I mean, we cannot have any security breaches there. If you are doing autonomous driving and it's being controlled by somewhere, if there is a security breach, you can assume what happens. So this is the kind of stuff that we're talking about when we talk to 5G. So what happened in codes in 5G? We use some block codes, but mostly polar codes for most of the um, control channels, which replaces the convolutional codes of 4G. For data channels, we use LDPC codes replacing the turbo codes of 4G. This is mainly because of the error floor, as I told you before. It doesn't really have an error floor. And that is why, they used to find applications in magnetic recording. So in data storage, LDPC was used way before it was used in wireless communication. And that is because they couldn't tolerate an error floor. That's why they did use turbo code, because when you do data storage, you can't do error floors. And with MIMO, there is a whole different thing that I won't get into MIMO too much. I'll just touch upon MIMO in the end a little bit. And I will touch upon these two codes in some amount of detail. So when we talk of LDPC codes, LDPC codes was actually invented by Gallagher in his PhD dissertation in MIT in the 60s. And it was ignored for many, many years simply because it was thought to be impractical. The memory requirements to decode these codes were quite large, and it was not thought that it was feasible to do it on a chip. But for present-day technology, it's extremely practical. Now, performance, if you just take plain performance, you could possibly find a turbo code and LDPC code where the waterfall curves looks exactly the same, except for the error floor. So the turbo code will typically have some error floor, but LDPC will continue to follow the waterfall shape. The decoding trades memory for computational complexity. The encoding part, finding good codes, is again another issue. Both in turbo codes, finding good codes now is fairly easy. I mean, there's a very well-defined body of literature as to what is a good interleaver, as to what kind of RSCs do well, both for serial and parallel turbo codes. And so that's not a problem. In LDPC, there are two kinds of LDPC codes, and I'll get into that when I come to it. So one kind is a regular LDPC codes, and the other kind is an irregular. Now, the whole thing is that you can regard LDPC as a block code. However, the parity check matrix is very sparse in the sense that it's mostly zeros. There are only few ones present in the parity check matrix. And we use this structure optimally to decode that. Each equation, so in a regular LDPC code, what happens is every code digit is maintained in the same number of equation, and each equation contains the same number of code symbols. With that happened, there are well-known design techniques of LDPC codes for regular LDPC codes. Now, irregular LDPC codes, relaxes these, so you can have the metric should still be sparse, but you don't have to have these regularity conditions. And then it becomes more an art than a science, because how to find codes which are optimal in such a case in a large block length is quite interesting. Here is an example of an LDPC code where this is a 12.5 code. Obviously, remember that LDPC codes are not really used for these block lengths. These block lengths, you're much better off using some kind of a block code, because optimal block codes for each block length are known. For each NK, Mac Williams and Sloan's, for example, in his book, does a wonderful job of giving you what are the best codes for each block length. And they have very efficient decoding algorithms. But to illustrate a very long code becomes hard. So let's just, this conveys the idea as well as anything else. Here you will see that each code symbol is contained in exactly 3 equations. So if you look at C1 is contained in equation 2, 5, and 7. Okay, and so on and so forth. So you for each each code word, you can see that they're involved in exactly 3 equations. So the number of ones on each of these columns, if you look at it, on each of these columns, there are exactly three ones in each column. Each equation involves exactly 4 code symbols, and there are 7 independent equations for the 7 check bits. I'm sure it should be bits, if not bits, and 5 information bits. Now, irregular LDPC codes was introduced in ISIT 98 in Sorrento, if I remember right, by Luby and all, where there are variable number of ones in rows and columns. And they did it through a technique which is known as density evolution. It will take me a little too far or too much time to go into that, but if you're interested, you can look up this technique. And they seem to perform better than LDPC codes, and also they can give unequal error protection to some bits. They have some parity equations which give more reliable information and hence gives decoding a jump start. So you can think of that in LDPC codes, what happens is that we decode each of these bits and then pass these bits onto the other bits and try to decode them. And roughly, there is no preference that all of these bits initially at least start with the same level of confidence. Here, you can say that certain bits start with a different level of confidence. And so in a successive interference cancellation procedure, these bits are more reliable and hence they jumpstart the decoding procedure. So how do we decode them? Decoding is known as a message passing algorithm, where a bit node and a parity nodes are shown here, where bit node is shown by 3 lines connecting to these parity nodes, where each of the squares represent a parity equation and each of the circles represents a code word. So you can see we can form a graph and we can pass these messages along the line of a graph. So what do I do at each node? We obtain the LLR. So what is the probability that CI is 1 or 0? We take the ratio of this, take the log of this, which is the log likelihood ratio or the solved decision for each code bit, and then pass it along this, and using that and using the probability of this being 1 or this being 0, we can recalculate the probability at each stage of message passing to form new estimates. Once we form these new estimates, we have to renormalize them because of the way this is done. Essentially, that we still got to make sure that they're a probability distribution. And I unfortunately, the time is too little for me to go into the whole mathematical details of this, but LDPC codes are well known and well studied, and this message passing algorithm and including this normalization at each stage is fairly well known in literature. So you can look that up. What is interesting to us is how this is done in 5G. The kind of codes that are used in 5G are so-called protograph codes. Protograph codes, what is a protograph code? Basically, there's a base graph. I mean, the codes in 5G, if you think about it, 3G, 4G, 5G, what have you, for large block lengths, if you look at the probability of error as a function of block length, you will see that the curve sharply decreases and then plateaus out. Where does this plateaus out? It plateaus out somewhere between 3,000 and 6,000 bits. And then you really need a huge number of bits to double them to get any lower. So if you look at, that's why most of the block lengths that you see, that the turbo codes, for example, in WCDMA or CDMA 2000, are split up into a bunch of blocks. Each of these blocks are 3172, 3072 in size, corresponding to the 3000 block number. So that if you have a very large data length, they're split up into these blocks, and the turbo decoder works on each of these blocks so as to minimize the complexity. Otherwise, the complexity for the turbo decoder becomes very, very large as the block size increases. In LDPC, similarly, for decoding, if the block size becomes very, very large, you will have a very large memory requirement. Again, the processing power is not that much, but the memory requirement is very large. So what is done is we do a protograph code where we have a base graph. This base graph is what is known as a protograph, and then they're so-called lifted. By lifted, we mean that the connections of the graph are changed in the way that is shown in this figure. Uh, so, so basically, from the base graph, you obtain a new graph through this process of lifting, so that it leads to an efficient decoding algorithm. The base here, there are two sizes of base graph size 1 and size 2 with two different mother code rates, as I've written down here, as you can see. And then these are decoded with the message passing algorithm. So that's what forms the base of LDPC codes in 3G. With polar codes, which
Sandip,
was
one quick
introduced
question.
by... Yes. Yes. I'm sorry, you're breaking up. Say that again, please.
About let's say, okay. No, I have seen the new radio thing.
I'm sorry, I cannot hear you. Is there a chat window?
Okay.
Did anybody else hear the question and can relay it to me?
Lalita, it's the same case with me also. I'm not able to hear you properly.
Yeah, I can hear you properly, but I can't hear whoever asked the question. I can't hear her properly.
Okay, so maybe we can wait Lalita to type in her question.
Yeah, that would work.
Okay.
Yeah. So I'll continue, and I'll leave 15 minutes in the end for questions anyway. So you can ask that question again. Or if your connection becomes good, ask me again. Your polar codes, which were introduced in 2008, are shown to asymptotically achieve capacity. At low block lengths, though, the performance is quite mediocre. So the original decoder that was used is a successive cancellation decoder, and the list decoder, successive cancellation list decoder, introduced by Tal and Vardy in 2015, improves the performance at low block lengths. And this is really what led it to being introduced in the control channels of 3GPP, because the original thing that was there was very good for large block lengths, but not so good for small block lengths. So if anything, it should have been used for large block lengths instead of LDPC in 3GPP, but the decision was to put it for control channels. So there, this SCL list decoder made it possible. And the reason it was used for the control channels is I'll come to it shortly, is because it also helps in a very quick decoding. So as you know, that in OFDM systems, you have to have a control channel and a data channel. And the control channel, you first decode the control channel, because there is no dedicated data channel to you. There's no circuit switch path. It's all packet switched. Since it's all packet switched, at any point, you don't know whether the data is meant for you or not. So every time there is data for you, there has to be a control channel which tells you that there is data at such and such a place waiting for you. You go and get it. So the way to get that is you decode this control channel. If it is for you, you then go and get it. Now, it's important that it's not only one kind of data that is being sent to you, there are multiple kinds of data. So you have to decode many, many control channels. So when you're decoding this, it's good that you can decode it very quickly. The quicker you can do it, the better it is for you. And this is where it helps. This one CRC embedded codes, polar code really helps. How does polar codes work? It works by polarizing the channel. So what is polarizing channel? It's pretty much similar to what you think of polarizing a light. So if you think of that two waves, which when put on top of each other, if they're constructively interfering, they have a very bright spot, like a Young's two-slit interference deflection kind of thing, or they have very dark spots. So if you look at a communication channel, with a certain probability, what you see is that ergodically, if you look at these ergodic channels, at any point, if your channel capacity is C, certain channels are good and certain channels are bad. In the sense that certain channels, if you send one bit through, it will go through, and in other channels, it won't go through. So in a sense, you can think of them, if you think of all the ergodic representations as some kind of a wave, where the probability of a one passing is higher in some channels than in other channels. Now, if I can somehow or the other do the following, that I take a set of bits, convert them into a vector, and then aggregate these channel capacities in some way, and then disaggregate them back again, such that I'm sending my information through the good parts only, that is places of positive polarization. Okay, then I can do something good. Now, so what I do is basically create parallel virtual channels somehow and use the reliable ones and set the remaining ones to 0 or the frozen set. So what I'm doing here is I'm doing n copies of 0, 1, which is a vector channel. We are splitting up the vector channel into reliable and unreliable, where each transmits 1 bit. And Gn is a random permutation. Now, the question, of course, is that how do I know which one is polarized well, which one is polarized badly? Well, what it says is that as long as you make large enough and do a random permutation, you will achieve good polarization. This is in very similar, the proof of this, if you look at the proof that was provided, in very ways, the spirit is extremely similar to the proof Shannon provided of random coding. If you look at his proof of random coding, you will see that, as the block size increases, a random code will achieve capacity. Because in probability, I mean, there are parallels in real life. If you look at a Rayleigh fading channel, there are very often deep fades, but most of the time the channel gains rather than going into deep fades. Okay, and as a result, the average is still below 1, but very many times that it's actually positive. And this is what we used in our scheduling algorithms, that we try to schedule people when they're in a good channel condition, so that the effective data rate of the system increases. And this is not much different from polarization, or not much different from this channel capacity business, where we are trying to do exactly the same thing, except that there's no feedback. Since there's no feedback, we can prove that for very large lengths, this GN, a random permutation, will do for you. Now, the actual channel capacity is somewhere between the middle of these actual channels. However, if you just put in a random encoder there, just like Shannon's random encoding, it becomes difficult to decode or encode, especially when n becomes large. So this is not very practical. While this may be a good theoretical tool, it's not practical. So what et al. Did was very, very smartly realized that if you take this matrix G2, which is this 1110 matrix, and take two parallel channels, okay, and take two independent bits and pass it through these parallel channels, the effective mutual information of this is the same as the effective mutual information of those two parallel channels. Now you can use this matrix and take the Kronecker product of it with itself. So if you take an n-fold Kronecker product, you get a 2 to the power n code words. So you can form an NK code in general by using this generator matrix n. In 3GPP, what is done is for uplink, this n is between 5 and 10, and for downlink is between 7 and 9. And in addition, we put a bit reversal permutation matrix. As we saw, that any permutation matrix still preserves the properties of the code. So a bit reversal permutation matrix does not change the property of the code in any way. And so it becomes symmetric, it becomes similar to a block code where this extra bits, so it's a 2 to the power n nk code. So you have a bunch of extra bits there, and they're all frozen to zero. So this becomes easily scalable and gives for an effective algorithm. So here is a polar code example. You will look at the structure and see that this is much like a Wald-Hadamard structure, So all the decoding algorithm can use a very similar structure, where we have a bunch of bits that are frozen. So if you are trying to do a rate half n equal to 8 code, so 8-4 code, we have to freeze 4 bits. So these 4 bits in 3GPP, since bits are frozen, you might as well freeze them to 0. Okay, so all frozen bits are 0. And then you can take all the free bits and put your whatever information you have on it and send it on the channel. The way to decode is we go from the left to right, in successive decoding cancellation. So at each leaf node, you calculate what is your log likelihood ratio, which is obviously given that y1 to y8, what is the probability that you receive that, given that your leftmost leaf, which is equal to 1 or 0, whether it's 1 or 0. Now, if it is frozen, we know it is 0. Okay, so it's done. But if it is not, then the hard decision is, if the log likelihood is greater than 0, I choose it to be 1. If it is less than 0, I choose it to be 0. Now, I know the frozen bits and this decoded bits. Then I use that to do a successive cancellation on the remaining bits. So I take that decoded bit and use a LLR based on that bit, and then successively decode the remaining bits. As n increases, this achieves optimal capacity. But when n is small, the probability of error is given by this. It's an order of 2 to the power minus square root of n plus an order of square root of n. So in a small one, we do a trick which is similar to the VITERBI decoding, where instead of keeping only one path as this stage, remember in this here we were only decoding the leftmost node. We were decoding this only first, and once we decoded it, we took the hard decision and took it to here. Now at each stage, instead of keeping just one path, we can keep L paths. Okay, so this is what is known as a successive decoding list encoding. It's similar to the dynamic programming of VITERBI decoding, but obviously with a difference, because you don't do successive cancellation in VITERBI decoding. And the complexity becomes a little more. It was n log n before, it becomes order of ln log n, and it quickly approaches the maximum likelihood decoding bound, as you can see from this curve. This is taken from Tal and Vardy. In 3GPP, what we also do is that we do CRC aided polar codes. Now, if you look at the structure of the CRC, you will realize that if you have k information bits, then and you pass it through a block decoder, an encoder, then the first bit becomes irrelevant after a certain point, because all the parity bits that you have used to encode the first bit is gone, and there is no memory. There's no linear shift register in there after that point. The bit has gone out of it. So basically, after that point, the first CRC bit will not change. So after the effect of the first CRC bit is over, we can effectively put in the first CRC bit. Then after the effect of the second is over, we can put in the second CRC bit. So instead of having all the CRC bits in the end, we can distribute them along the codeword. What does it do? Well, if any of these CRC bits don't pass, you know that you have made a mistake. So you can quickly abort the decoding. So where speed is such an issue, you can quickly abort the decoding faster. Okay. So you can append as soon as this dependent finishes and adapt to that to quickly decode them. And on top of that, you can obviously adapt to the data rate by the usual things of interleaving, rate matching, and hybrid. So this is roughly what polar codes are, the form that they're used. I'll spend 5 more minutes on MIMO, not too much more. So MIMO, as you all know, is that there are N transmitter and N receive antennas, and they're sent over a wireless channel. They can either be open loop where there's no feedback, or closed loop where there's the feedback. If you look at the diversity schemes, there are 4 diversity schemes with different capacity. The size of capacity is, of course, Shannon's formula. With transmit diversity, you see that you get an increase because the number of HIs, which are your normalized channel gain, increase to M if you have M transmit antennas. The receive antenna, the receive transmit diversity is obviously more. The capacity is higher in receive transmit diversity than transmit diversity. Yet, for the most part, you will see that the initial transmission systems only use transmit diversity and not receive diversity. Why is that? Well, essentially because all the MIMO was down on the downlink, not on the uplink. On the downlink, your transmitter is the base station, your receiver is the mobile station. And mobile station cost is dominated by the RF chains. So to put in another antenna and hence another RF chain on the mobile initially was very costly. And since cost was directly borne by the consumer, it was not widely done. Whereas at the base stations, which are only much lesser, and it's anyway a large infrastructure cost equipment. The cost of adding an additional antenna was totally worth the extra data rate that it brought. That is why transmit diversity was used in the initial. And finally, you are well aware of the MIMO capacity. So for transmit diversity, if you look at that, Alamoti code was the one that was used, or certain variations of it. Initially, the Alamoti code was used in the time domain. So two successive symbols would be coded in a certain way. Then you can adapt it to the frequency. Instead of for OFDM systems, instead of doing it across two time symbols, which means that the number of symbols have to be even or you have to wait longer, you can do it across two frequency OFDM symbols. You can do the same thing. So that is what it was done and was known as SFPC, space frequency block coding. If you look at MIMO, you will see that at low SNR regime, typically in OFDM, I would say below 7, 10 dB, somewhere in that range, MIMO really doesn't gain you a whole lot. It does gain you beamforming gains. So if you can do beamforming, it does gain you gains, but otherwise no. But when the rate becomes higher, so when your SNR becomes higher, say 20 dB or so, then you see a significant amount of gain. In particular, I mean, you can have double the capacity when you have enough rank in the channel. So your rank of the channel typically increases as you become higher. So classically, there are two ways you can have one coded and interleaved bit and spread them across and scramble to a CR blast architecture. That is not used in 3GPP or CDMA 2000. What is used is separate coding and multiplexing chains, which are known as special multiplexing. So each code you take, split it up into parallel codes, split it up into parallel streams, and code and interleave each stream and send it over. So in general, if you have a 4x4 MIMO system, the optimal thing to do to achieve capacity, as it can be shown, Telitar and all, that you need to split it into 4 streams. However, and so you need 4 independent codings. However, it was only 2 is done for the sake of complexity, because you need feedback on these to see the reverse water filling, as you are well aware, to achieve MIMO capacity. You need to know how much on each channel you should send. The feedback has to be sent on the reverse link for each of these channels, and the larger the number of these in each individual stream that you're going to send, that is each individual code word, you have to have that feedback. And that kills the uplink, because we are very often uplink limited. So the conscious decision in 3GPP was to do only 2 streams. In LTE, there were 7 transmit modes initially, and then there were others, which included SISO, transmit diversity, open or closed loop, a very Stone Age SDMA, as we used to joke, and then some beamforming modes. Now 5G MIMO is mandatory on both links. There is all these modes have been dispensed with. MIMO is mandatory, and basically what we have done is moved over to massive MIMO, essentially because at high frequencies, the size of the antennas become very small and the propagation characteristics are really bad. So massive MIMO is used gainfully to still provide reasonable amount of communication. We use a successive cancellation receiver, and again, all of you know this, so I don't need to do much. You do nulling, detection, interference estimation, cancellation, and iterate to look at the final solution. So what did we talk about? We talked about how coding has evolved over the time in 3GPP systems, and we saw how we arrive at the various things. So I'll leave the remaining time to questions. So whatever questions you have, please do, and I'll try to answer to the best of my knowledge. Yeah, go ahead. I'm done. Floor is open.
Sandip, I think there are a few questions in the chat box also.
Oh, okay. Okay, I see.
So if you want, I can read them out.
How do I see the chat box? I'm not entirely sure how to see the chat box. If you don't mind reading them out, can you read out the question and then?
Sure, sure. I think one question was that I've seen LDPC codes in 5G NR. How are the cyclic shifts determined to get to the LDPC code construction? Is there a systematic way?
So this is the process called lifting that I said. So what is done is that there is a base graph, and from the base graph, since this is a protograph code, as I showed you. So let me go back to that particular one. You can still see my screen, right?
Yes.
Okay. So yes. So if you look at this LDPC in 5G, what is done is there is a base graph, okay, which is known as the protograph. So you have some bits and then some parity bits connected through a particular graph structure. Now, suppose what I do is repeat this graph structure 4 times. In one, repeat this graph, and then instead of connecting to those nodes, connect to some other sets of nodes so that the number graph edges do not change in this way, okay? So this is how they're constructed. And again, not all liftings will give you a very good code. So enough number of experiments were done. Tom Richardson, during his days at when the flash OFDM system was introduced, he first came up with this technique of doing so. And then this was then subsequently adopted for 5G and so on and so forth. So this is how it is done. There's a large amount of literature. Look up some of Tom Richardson's publication for the original ones, and then if you just look up protograph codes for LTPC, you will find a whole lot of literature out there in the market. Yeah.
Yeah. So another question in the chat box is, why is CR blast not used in practice?
So that was a decision. That was a decision that was made. What was found is, for the most part, the performance of successive interference cancellation decoding was better than CR blast. And why? If you want an intuitive explanation, there is not such a good explanation all the time, but I'll try my best. Okay. In CR blast, what happens is there is only one code word, and the feedback you send is 4 code word each in So if you are off on that, you are off by a large amount. And what happens is that if you look at the coherence time of a channel, if you take, say, your Doppler frequency is FD, or where your carrier frequency is FC and you're moving at a speed v, then it's v by c times FC is your Doppler frequency. A rule of thumb in wireless communication is that your coherence time is 0.2 by FD. If you calculate these coherence times for various things, you will see that the coherence times is quite small. So by the time your feedback comes and you are sending this data, your coherence time has very much changed unless you're traveling at very, very low speeds. So the errors that were introduced across the board due to this were quite large. If you had one code word, with 2 code words, it was somewhat slightly better. And the successive interference cancellation led to some of the better decoding techniques and better decoding performance. So roughly that is why the decision was made to go with spatial multiplexing rather than PART. Thank you. Any more questions?
Yeah. So maybe one question is so related to these LDPC codes. I guess one kind of complaint against them was that the encoding complexity is a bit high. It's of order n squared if you do it naively, right? So are there any sort of special techniques used in practice?
So this protograph code, makes the encoding much lower, right? Because now you can see that this lifting business, what you have to do is the base graph, there's nothing you can do, okay? The base graph you still have to do. But from the base graph, now you can use a recursive structure to generate this, right? just as we do for Wall-Schadron coding and stuff like that. So that is one thing that is there. And the other thing, of course, is that irregular LDPC codes, finding the base code is rather difficult. It's not a simple technique. With density evolution and all of this also, it's not straightforward. But then you only have to do it once. Once you have done it and put it in the standard, you don't really care after that, right? So that's okay. Does that answer your question?
Yeah.
Yeah, good.
So any more questions from the audience? Please type it in the chat box. Sandeep, can you hear me now? Is it better?
Yes, I can hear you perfectly.
Okay. Okay. Now, we had a question about, I mean, whether LDPC codes have error floors or, what are the parameters which affect the error floor, let's say.
So
I mean,
LDPC code really doesn't have error floors.
okay.
Yeah, that is one of the big things about LDPC codes. I mean, in the all regimes of interest, there is no error floors.
Okay.
Yeah. And really, to be honest with you, why turbo codes have an error floor is not also perfectly well understood. And how this error floor happens. It's all part of the decoding technique. I mean, it's totally possible that with a different decoding technique, turbo codes don't have an error floor. But those error floors are part of that decoding technique. And it's not fully understood why this iterative technique, first of all, converges in some cases, doesn't converge in other case, and what error flow it leads to is not perfectly understood yet. At least not to my knowledge. It may be, some people may know, I don't know. I have not seen anything yet that explains.
Okay.
Yeah.
So is there any unifying, there's one question which asks, is there any unifying, principle of these three codes that we have talked about, like turbo, LDPC and polar, or do we have to, think of them completely separate?
I mean, no, I mean, to my mind, they're separate. I mean, really, the turbo code works on the principle that the decoding is also very, very different. The decoding, we do a map decoding for turbo codes, bit by bit map decoding. For LDPC codes, it's kind of a message passing algorithm, a one-shot thing where we take a set of error probabilities and then use the structure of the graph to get the next. I mean, really, the unifying thing, of course, is that I think if you not unifying, I don't know, but if you really think of it, in spirit, the closest any code comes to Shannon is polar codes, because really much of the polarization business is very similar to what Shannon had in his original ideas about this random coding. It's really same, but then coding theory, I mean, was solved, right, with Shannon's random code. But the whole point is finding reasonable codes with a good decoding algorithm that does well. And that is where this whole business lies. So it's all different approaches to find this optimal encoding and decoding. And these three are totally three different approaches. I don't know if there's a unifying one. Maybe if some of you know, I would love to know.
Okay.
Yeah.
Yeah, as of now, there are no questions. I had one question about block codes. You kind of mentioned that block codes work. I mean, in the current, let's say they work for code lengths of less than 50 or so, right? Is there a chance that in the future, like let's say they can start working up to, let's say, code lengths of 200 or so, like now or wherever convolution codes?
Absolutely, no question. For for each given an NK, okay, there is an optimal block code for each. No question about that. Any of these codes, a LDPC code, a turbo code, what have you, you can always regard them as a block code, right? Because you are taking n bits and forming, you are taking k bits and forming n bits out of it. You can always write a generator matrix for that. The whole question is there an efficient decoding algorithm or an efficient encoding algorithm, right? That is the whole question. So obviously, whatever LDPC code or whatever turbo code you used, I'm sure you can find a block code if you were to just do a brute force search with time being no factor. You can find a block code which will do better than that. The question is, can you decode them better? Because the decoding algorithms that are there for the block code which is syndrome decoding. That's what we do for block codes, right? Which becomes very, very difficult when this becomes harder, when it becomes larger. Otherwise, we would do a Golang code for everything, right? The Golang code is the perfect code. You can't do better than that, right? Because if you look at vector quantization in space, that's the perfect code. However, decoding them, encoding them becomes a challenge. That's the whole thing. So now, to partly answer your question, what was totally out of bounds years ago is totally in bounds now, right? So LDPC code, nobody could do it at that point. Turbo code would have been virtually impossible to implement in the 50s, right? With what we had. Today, turbo codes are easy to implement. What is there to say that 50 years from now, block codes of any size won't be easy to implement? It might well be, and then why not? But as of now, no. As of now, depending on where we stand, putting a block code that we don't know of a block code with a good enough decoding algorithm at those lengths to be able to do so. That is the only thing.
Okay. Yeah,
yep.
Sure.
Yeah.
Any other questions from the? Okay, if not, we'll thank the Sandip again for his excellent talk on a whole spectrum of code where they are used in different standards and 3GPP. Let's thank. I think I will thank. Okay. Thanks a lot, Sandip, for
thank you so
participating. Yeah. Okay. So,
thank you.